And the masked professor, once more, he picks up his leaden rapier. Hello, statistics fans. Oh boy, today I'm going to talk about how to create confidence intervals for proportional probability representations. All right, so now let's plunge boldly. I should have got the PowerPoint up already. Okay, detergent filling. Here we go. All right, so what I'm going to talk about is what we call the normal approximation for the binomial proportion. You remember that a binomial proportion means that it is subject to the Bernoulli trials, that there can only be success or failure, that all trials are independent from each other, and that there is a set proportion for that success or failure. All right, so if our sample size is large, the distribution z equals the quantity x minus np divided by the square root of np times the times 1 minus p is equal to p hat minus p divided by the square root of p times 1 minus p divided by n. Now, this looks almost exactly like how we figure our z number if we are looking at a regular z number type situation. For example, x minus np. Well, what is np? np is our mean, or mu. The square root of np times the quantity 1 minus p is just the standard deviation. Okay, so all we have to know is what is the tiny variation from looking at a z number in the regular way to looking at a z number in our binomial proportional world. All right, so we say that's approximately standard normal. Close enough for the government job. Our quantity, square root of p times the quantity 1 minus p divided by n, is called the standard error of the point estimate, p hat. All right, well, good on it. All right, so that implies that we can put together a confidence interval on a binomial proportion. Now, they say approximate confidence interval, but a confidence interval is always approximate. So, if p hat is the proportion of observations in a random sample of size n, an approximate 100 times the quantity 1 minus alpha percent confidence interval on the proportion p of the population is p hat minus z alpha divided by 2 times the square root quantity of p hat times the quantity 1 minus p hat divided by n less than or equal to P less than or equal to P hat plus Z alpha divided by 2 times the square root quantity of P hat times the quantity 1 minus P hat divided by N. Again, this is where Z alpha divided by 2 is the upper alpha divided by 2 percentage point of the standard normal distribution. Okay, so nothing super new about this, except now we're working with the binomial proportion. All right, so our example here is about crankshaft bearings. In a random sample of 85 automobile engine crankshaft bearings, 10 have a surface finish that is rougher than the specifications allow. Kind of important with crankshaft bearings. Construct a 95% two-sided confidence interval for P. So our point estimate of our proportion of bearings in the population that exceeds our roughness specification is P hat equals X divided by N. X is the defective or too rough bearings. N is our sample size. In this case, it's 10 divided by 85, which works out to be about 0.12. A 95% two-sided confidence interval for P is computed then from our equation 811 that we saw on the last slide. So we say it is P hat minus Z, boy, you can barely see that's a Z, Z of 0.025 times the square root quantity of P hat times the quantity 1 minus P hat divided by N is less than or equal to our binomial proportion is less than or equal to P hat plus Z of 0.025 square root quantity of P hat times the quantity 1 minus P hat divided by N. Boy. All right, so now we just substitute in our numbers. We know that P hat is 0.12 from the calculation done up here. We know that Z of 0.025 is 1.96. We put in P hat 0.12. 1 minus P hat is 0.88. We divide that by N, which is 85. That's less than or equal to P, our binomial proportion, less than or equal to 0.12 plus 1.96 times the square root quantity of 0.12 times 0.88, 1 minus P hat, divided by 85. So we get a proportion that is 0.0509 less than or equal to our binomial proportion, less than or equal to 0.2243. So in other words, our proportion of bearings that are too rough is between 5% and 22%. This is a wide confidence interval. I think we all recognize that. Our sample size is not small, right? It's N equals 85. The value is fairly small, and so we have a large standard error. All right, well, one thing we want to really think about in terms of determining these confidence intervals for a binomial proportion is what is the sample size that we need to get a good answer. I have no doubt, so sample size for specified error, if we set E equal to Z alpha divided by 2 times our standard deviation, square root quantity of P times the quantity 1 minus P divided by N, and we solve for N, we get an equation that looks very much like the sample size equation that we use for a regular standard normal distribution problem, right? N equals the quantity Z alpha divided by 2 divided by E, that quantity is squared, times P times the quantity 1 minus P. Okay, how could we make it simpler than that? Well, of course we could. Now, the thing about P times the quantity 1 minus P is that it has a strict limit on how far, how big a number that can be. So our sample size will always be a maximum at P equals 0.5, which means that P times the quantity 1 minus P is less than or equal to 0.25 when P is equal to 0.5. So we can always use 0.25 here, right? So that would be sample size equals the squared quantity of Z alpha divided by 2 divided by E times 0.25. All right, so we can always use this when we're working with binomial proportions. And I'll demonstrate that a little bit later on in our talk here. All right, so we extend our example of crankshaft bearings. So we consider the situation in example 8.8. How large a sample is required if we want to be 95% confident that the error using p hat to estimate p is less than 0.05? All right, well right now we have a p hat equal to 0.12, right? 10 out of 85 crankshaft bearings. That's our initial estimate of P. And so we look and we say the required sample size, N equals Z of 0.025 divided by E, that quantity is squared, times P hat times the quantity 1 minus P hat, and we substitute in our numbers. We know that Z of 0.025 is 1.96. The error we don't want to exceed is 0.05. That quantity is squared. Then it's times 0.12 times 0.88. And we get that that is approximately 163. I'm sure if we worked it out with our calculator, we'd get 162.7 or something like that. But you can't have 0.7 of a sample. Again, we must always round up to the next number. So if we wanted to be 95% confident that our estimate p hat of the true proportion was within 0.05, regardless of our value of p, we would use our equation 813 to find the sample size. So in other words, instead of using p hat times 1 minus p hat, we would substitute in our 0.25. So n equals the squared quantity of z of 0.025 divided by e times 0.25. We substitute in our numbers again, and we get that we have to have a sample size of 385. Wow! So, sometimes it's advantageous not to use our 0.25, but to use our actual p hat. So, if we have information about what is our binomial proportion, that might be from a preliminary sample, from past experience. Very often in industrial settings, we keep a running total of where our binomial proportion is in our industrial setting. We can use a smaller sample while we have the desired precision and a good level of confidence. All right. Now, of course, like anything else, we might want to have a one-sided confidence bound for our binomial proportions. So the approximate 100 times the quantity 1 minus alpha percent, lower and upper confidence bounds are p hat minus z alpha times the square root quantity of p hat times the quantity 1 minus p hat divided by n is less than or equal to p, right? In the case of our crankshaft bearings, we might want to use, however, the upper bound formula. P is less than or equal to p hat plus z alpha times the square root quantity of p hat times the quantity 1 minus p hat divided by n. Okay, so as usual, really we've just broken our two-sided confidence interval up, and we have z alpha instead of z alpha divided by 2. Now, there are other ways that we can get a better and better interpretation. However, in this class, not going to worry about it. This slide is an extremely helpful one. In this one, when we're going to construct our confidence bounds, if you use this table, it will help you decide what distribution you need to be in, right? So, for example, we want to find the mean of a normal distribution, mu. Well, if we know the standard deviation, then we go to section 8.1 and we use the formulas there. If we're looking at the mean of an arbitrary distribution, but we have a large sample size, we're looking for mu, our sample size is large enough that we consider the central limit theory to apply, and our standard deviation is essentially known because we're just going to use our sample standard deviation. All right, in that case we go to 8-1.5. We might be looking for the mean of our normal distribution, mu, and we're looking for, we don't have a standard deviation, sigma. It's unknown, and we're estimating it. In that case, we're going to go to the t distribution and use that. If we're looking for variance or standard deviation of our normal distribution, we're looking for sigma squared or sigma. Our mean or mu is unknown, and we estimate that from our data. And we proceed from there. In that case, look in section 8.3 of your book. And for population proportion P, are there other parameters? No. We're only looking at P and P hat in that circumstance. And that's the section that we have just done. All right. So what I'm going to do now is I'm going to do some handwritten examples so that you will be able to follow along, because of course I'm going to post these handwritten samples on Moodle for you, so you can print those out and follow along while you're watching this to see how those are done. And hopefully that will give you the tools you need to be able to do problems on Wiley Plus that will be assigned for this. All right, how exciting is this? So let's switch back to camera. All right, and of course we have a lovely picture of an old book that we're not even using now, although it's from this same situation. It's just an older edition of the book we are using. All right, so I've got my Z tables here ready to go in case I encounter numbers that I'm not familiar with. The thing is, as you do more and more statistics, you're going to discover we almost always use the same numbers, whether they're when we're talking about the standard normal distribution, right? If we have a 95% confidence interval and we're using Z alpha divided by 2, it's always going to be 1.96. If we're using a one-sided confidence interval at 95%, it's going to be 1.645, or you could put 1.64, 1.65. Oy vey, I'm not going to get totally excited if you use any of those numbers. All right, so let's start with the proposition that how do we know that P hat times 1 minus P hat can be approximated by 0.25? All right, well, let me build a little table. All right, so I've got my P over here, and then I have my P times the quantity 1 minus P, and I'll put that here. All right, well, what if P is 0.1? That means that this is 0.1 times 1 minus 0.1 is 0.9. And what is that going to be equal to? Well, that's going to be equal to 0.09. At 0.2, that's going to mean that we're multiplying 0.2 times 1 minus 0.2 is 0.8, and that's going to be equal to 0.16. All right, I can see you're getting excited. Psychically, I can see that. Since obviously I'm here by myself. All right, now, what if our proportion is 0.3? Well, then it's going to be 0.3 times 1 minus 0.3, which is 0.7, which is going to be equal to 0.21. At 0.4, that means that 0.4 times 1 minus P, so 1 minus 0.4 is 0.6, is going to be equal to 0.24. Then we have 0.5, which means that 0.5 times the quantity 1 minus 0.5, oops, not 4, 5, comes back to me now, like the hot kiss at the end of a wet fist, is going to be 0.5 times 0.5 equals 0.25. All right, so what's going to happen if I go higher than 0.5? Well, 0.6 is going to be the same as 0.4. So that's going to be 0.24. 0.7 is going to be the same as 0.3, or 0.21. 0.8 is going to be the same as 0.2, which is going to be 0.16. And 0.9 is going to be equal to 0.1, which is 0.09. So most of the time, using 0.5 is a really good approximation, except when we get out to these extreme ends, where it might make a difference to calculate using p hat times the quantity 1 minus p hat, or p times the quantity 1 minus p. All right. You know, I started with a huge wad of paper here, and boy, I am getting down towards the end. But have no anxiety, troopers. We will continue on. If I have to, I'll go get more paper. All right, so I have a bunch of problems here to do. The first of which would be problem 8-5-3. All right, so 8-5-3. First of all, what are we given? The fraction of defective integrated circuits produced in a photolithography process is being studied. A random sample of 300 circuits is tested. All right, so that gives us our sample size, 300, revealing 13 defectives. So I could say that is X, which is how we usually do it here. All right, so that makes it pretty simple. Then part A, we are going to calculate a 95% two-sided confidence interval on the fraction of defective circuits produced by this particular tool. Okay, well, photolithography is a process that was, I think, first used industrially by Texas Instruments. That you could take a picture of a circuit and then by treating it with various chemicals, you could actually make that circuit on your picture. I could be wrong about that because I have degrees in mechanical and industrial engineering and not electrical engineering. All right, so we know that for a 95% confidence interval, two-sided, that implies that our, oh, bloody hell, should have started on the next line. All right, so 95% confidence interval, two-sided, that implies that Z alpha divided by 2 is equal to 1.96. All right, so this is part A. We calculate our p hat as being equal to x divided by n. And x we know is 13, and n is 300. All right, so pardon me a moment while I fire up the old Excel. And we go equals 13 divided by 300. And that's equal to 0.0433 repeating. All right, well, we want a two-sided 95% interval, so that's p hat minus Z alpha divided by 2 times square root quantity hopefully I've made that large enough, of p hat times the quantity 1 minus p hat divided by n less than or equal to our binomial proportion less than or equal to p hat plus z alpha divided by 2 times the square root quantity of p hat times the quantity 1 minus p hat divided by our sample size. Okay, well, how exciting is this? So, I am going to truncate our p hat a little to 0.043. So 0.043 minus z alpha divided by 2, we've already determined is 1.96, times 0.043 times 1 minus 0.043. Didn't make my radical sign big enough. And that is divided by 300, which is less than or equal to p, and that is less than or equal to 0.043 plus 1.96 times the square root quantity of 0.043 times 1 minus 0.043. Damn it, I'm not making my radical signs long enough. Divided by 300. All right, well, I quickly run over here and use Excel again. All right, equals my 0.043 minus 1.96 times the square root quantity of, all right, another left parenthesis, p hat times the quantity 1 minus, 1 minus p hat divided by 300. Okay, and they found a typo in my formula, and yes, that would correct everything, so go ahead and do that. So for my lower bound, I'm going to get 0.020. All right, 0.020. And for my upper bound, I have to fix it more than I normally would. Because usually I just put in the raw numbers. In this case, I went ahead and clicked on my calculation of p hat to put that in. All right, so that fixes all my numbers. So my upper boundary of my proportion becomes 0.066. All right. So, not too shabby. We have a proportion, a binomial proportion estimate between 0.020 and 0.066. Of course, if we were in the quality control department, we might say that's great, that's terrible. It kind of depends on the limits we're setting. But they say, what if we want a 95% confidence interval, but we want that on the upper confidence bound? In that case, that implies that our z alpha divided by 2 is equal to 1.645. Right? Again, you could use 1.64, you could use 1.65, and I'm not going to get terribly upset if you do. Okay, how do we take things from there? Well, we just do the same thing, only we're going to use the formula for the upper confidence bound. So we're going to say the proportion, the binomial proportion, is less than or equal to p hat plus z alpha times the square root quantity of p hat times quantity of 1 minus p hat divided by n. All right, easy peasy. Then we substitute our numbers. P hat is still the same at our, oh, sorry, what a mistake on my part. P hat is still the same as in the calculation for part A at 0.043 plus our z alpha, oh, what are you doing? Z alpha at 1.645 times the square root quantity, give myself plenty of room, hoping it'll be enough, 0.043, 1 minus 0.043 divided by 300. All right, so I go over here to Excel, and I again fix my equation. Oh, damn it. Right, and I put my Z alpha in there, and Bob's your uncle, and I get 0.063. So P is less than or equal to 0.063. Now, is this a good binomial proportion for our evil purposes? Well, it's certainly correctly calculated, but that would have to be decided at the company that is in the quality control department. All right. So, all right, so let's think about our next problem, and I'm just going to use the next one in the book, which is problem 8-54. As usual, I always write down what is given in the problem. An article in Knee Surgery, Sports Traumatology, Arthroscopy, on arthroscopic meniscal repair with an absorbable screw, results and surgical technique. We're given the APA citation of 2005, volume 13, pages 273 to 279, showed that only 25 out of 37 tears, or 67.6%. All right, so let's write that down. X equals 25 out of an N of 37, and they're saying that is a p hat. When they say 67.6%, that means 0.676, located between 3 and 6 millimeters from the meniscus rim were healed. Okay, well, good to know. Calculate a two-sided 95% confidence interval on the proportion of such tears that will heal. All right, so that is part A, and we want a 95% confidence interval, two-sided. That implies our Z alpha divided by 2 is equal to 1.96. Okay. We're going to start with our formula, which is p hat minus Z alpha divided by 2 times the square root quantity of p hat times the quantity 1 minus p hat divided by n is less than or equal to our binomial proportion less than or equal to p hat plus Z alpha divided by 2 times our square root quantity of p hat times the quantity 1 minus p hat divided by n. Okay. So, all right, so now we have our formula. All we're going to have to do is go back and substitute our numbers. So 0.676 minus 1.96 times square root quantity of 0.676 times 1 minus 0.676, and we divide that by 37 less than or equal to p, which is less than or equal to 0.676 plus 1.96 times the square root quantity of 0.676 times the quantity 1 minus 0.676, and that is divided by 37. All right, well, as usual, I'm going to cheat and use my Excel here. Equals 0.676 minus 1.96 times the square root quantity of another left parenthesis, 0.676 times left parenthesis 1 minus 0.676, right parenthesis, let's see, and another right parenthesis, and divide that by 37, another right parenthesis. Bob's your uncle, all's well with the world. So that means our lower bound is 0.525, less than or equal to p. Now, our upper bound once more is 0.827. All right, so we have our answer. Somewhere between 52% and 82% is the proportion of people who will heal from this kind of a meniscus tear. But of course, they can never just leave it at that. In part B, they say, calculate a 95% lower confidence bound on the proportion of such tears that will heal. All right, so 95% confidence interval, but lower bound implies Z alpha equal to 1.645. Right? Again, I'm not worried if you go 1.64 or 1.65. So our formula is that our binomial proportion hat, our p hat, minus z alpha times the square root quantity of p hat times the quantity 1 minus p hat divided by n is less than or equal to our binomial proportion. All right. Now's the time when I'm going to scrunch down a little bit. All right, now we just substitute in our numbers. 0.676 minus 1.645 times square root quantity of 0.676 times 1 minus 0.676 divided by n, or 37, is less than or equal to p. All right, so once again, all I'm going to do is use Excel to do my calculations. Oh, okay. And my calculation becomes that 0.549 is less than or equal to my binomial proportion. So that implies that at least about 55% of the patients will heal after surgery from this kind of meniscus tear. Well, good on them, I say. All right. Would there be a huge difference if we used 1.64? It would just move it up to 0.550. And if we used 1.65, it would just make it 0.549. Essentially the same calculation that we've got here. Right? So you can see why I'm not too concerned if you decide that you don't want to use 1.645. There's not enough difference in the numbers to make it worth getting all upset about. Well, you know, inevitably, we're going to do another problem, and this one is going to be on the sample size that we need Okay, well, enough foreshadowing here. This is page 4. The problem is 8-59. The Arizona Department of Transportation wishes to survey state residents to determine what proportion of the population would like to increase statewide highway speeds from 75 to 75 miles an hour from 65 miles an hour. All right, obviously this is a very old problem because if you've been to Arizona, you know that most highways are at 75 miles per hour. How many residents do they need to survey if they want to be at least 99% confident? All right, so given 99% confident they want to be at least 99% confident that the sample proportion is within 0.05 of the true proportion. All right, so that means our error term is going to be 0.05. All right, well, one thing that they don't tell us here is, should it be two-sided or should it be one-sided? So let's do both of those. So that means that if we say 99% confidence interval, two-sided, implies that Z alpha divided by 2 is equal to what? Luckily I've forgotten, so we'll spend a moment here with our Z, our standard normal distribution table. All right, so I'm looking for 0.005. Right, and that is just pretty darn close. In fact, that is closer than the next probability over. Okay, so I've got negative, oh man, maybe I should make this much larger. All right, so I've got negative 2.5 and I add negative 0.08. And that is as close as I can get to my 0.005 without doing a lot of abstruse calculations. And abstruse calculations, as far as I'm concerned, are the most boring kind. All right, so that implies that our Z alpha divided by 2 is 2.58. All right, of course, our formula P hat minus Z alpha divided by 2 times square root quantity of P hat times the quantity 1 minus P hat divided by N. Oh, wait, though, I'm looking for sample size. Never mind. So sample size formula is N equals, okay, maybe I should go back a little bit. Sample size equals, oh, what was I thinking? Is equal to our Z alpha divided by 2 divided by error, that quantity is squared, times our P hat times P times the quantity 1 minus P. Well, we have no quantity of P right now. In fact, we're looking for that. So what do? We go to our famous substitute where we say Z alpha divided by 2 divided by the error, that quantity is squared, times 0.25. This will give us the largest possible sample, but since we have no data at all to work with as far as what is our p hat, our point estimate for our binomial proportion, this will give us what we need. All right, so n equals our z alpha divided by 2 is 2.58. Our error is 0.05. We square that quantity times 0.25. All right, so n is equal, and let me quickly calculate that, equals our 2.58 divided by 0.05. That quantity is squared times 0.25. All right, so that gives us 665.64. All right, but of course, as has been pointed out over and over again, you can't have 0.64 of a sample. So instead, we write down the next number up, 666. Now, hopefully, those of you with a more religious persuasion aren't quaking in your shoes at this point. All right, so that is for a 99% two-sided confidence interval. But what if we want just a one-sided interval? All right, so we're 99% confident one-sided. Okay, if we're going to calculate that we want a certain, we want the binomial proportion to be above a certain a number, we would use this. All right, well that is going to imply that our z alpha, all right, so I have to get my, all right, so I want the closest number to 0.01 that I can get, and this one is just pretty darn close. I am not sure we can improve on that. So let me put this here where we can really tighten down on it. So that becomes our 0.01. Oh, wait, 0.01, not 001. Oh, what a mistake. Why didn't y'all stop me from making such a hideous error? All right, you couldn't have. All right, this one, let's see, this would be 93 away, and this is 170 away. So this is the one. All right, so I put my paper for the column, and then I put my paper for the row. All right, so it's negative 2.3 plus negative 0.03. All right, so that's going to be 2.33. All right, so 2.33. Oh, man, now I'm messing things up by being too focused in. All right. So now we're going to calculate our sample size. We're going to do it the same way that we did before, except instead of z alpha divided by 2, we're going to do it with z alpha. And so we substitute in our 2.33 divided by 0.05. That quantity is squared times 0.25. All right? And let me quickly zip over here. So quickly you can't believe it. All right, and that calculation yields 542.89. 542.89. But, of course, can we have 0.89 of a sample? No. No more than we can have 0.64 of a sample. So, we calculate that by rounding up to the next number, which is 543. Now, I'm very curious as to what answer they give in the back of the book. One of the things I love about these books is very often they have the answers in the back. All right, so they calculated it as a two-sided, giving 666 as the sample size that they would want. All right, so where are we sitting here? Troopers, I would do some more problems, except that I need to make one more class video for this week. And I'm hoping that the problems that we've done are sufficient for you to grasp what we're trying to accomplish here. So, let me go ahead and say, please, stay safe, stay healthy, and when the fields are white with daisies, we'll meet again.